All right, so good afternoon. So you'll have your exam on Monday on stoichiometry, so everything from chapter 4. Um, so in a way, this exam is almost like an extension of chapter 3, right? Last chapter we learned about chemical reactions. This chapter is still dealing with chemical reactions. However, we're dealing with the math that pertains to chemical reactions. So stoichiometry is just the quantitative analysis of chemical reactions. So, and these problems should be pretty closely to what you should expect from the exam. A lot of these problems are just taken straight up from Alex. So, as long as you can solve these, you should be pretty good. So, number one here says that photosystems one and two in the chloroplasts of green plants capture and use light energy from the sun to drive photosynthesis, a chemical reaction in which liquid water So, a chemical reaction in which liquid water and carbon dioxide gas form aqueous glucose and oxygen gas. And I say to calculate the mass of glucose produced from the reaction of 0.07 moles of water. Okay, so um in doing stoichiometry, the very first and most important thing that you need is a balanced equation, right? So what's our equation going to look like? We have our reactants, right? Water and carbon dioxide, and it's going to make glucose and oxygen. So we have to write a balanced equation for this reaction. So we'll have 6 CO2 plus 6 H2O yields glucose and then 6 moles of water as well. Okay, so we write our balanced equation and now we can deal with the math. So I want to know the mass of glucose, so the mass of this that I can make from reacting 0.07 moles of water. Okay, so the only thing we can start with is the information that we are provided with, right? So we are first going to write down our 0.070 moles of water. Okay, now I need to get that to the mass of glucose, right? So hopefully you know that from watching the lecture videos and your discussion with the LA, the only quantity that can interrelate these different chemical species is the mole, right? So I'm starting in the moles of water. I want to end up with the mass of glucose. So I can't go straight from moles of water to grams of glucose. I have to go from the moles of water first, then to the moles of glucose, and then to the grams, right? So we're in the moles of water. How can I get to the moles of glucose? We do that by using the mole ratio, right? So the mole ratio comes from the balanced equation, right? So this equation says that we have 6 moles of water to 1 mole of glucose. That is our mole ratio, right? So I want the moles of water to cancel. I'm solving for the moles of glucose. So at this point, the moles of water cancel off. I'm the moles of glucose. From the moles of glucose, I can go to the mass of glucose, right? By using the molar mass. So now I want the moles to cancel. Then you just look on the periodic table, figure out the molar mass for C6H12O6. It's 180.16 grams. And then the moles of your glucose cancel, you're only left with the mass or the grams of glucose. Okay, so you just do 0.07 divided by 6 times 180. You will get an answer of 2.1 grams of glucose. Okay, and then you use 2.1, right? Because we have two sig figs in the problem and the number that's provided. So we have to keep two sig figs in our answer. Okay, so any questions about number one, going from moles to grams?
I think I'm all good. Thank you.
Okay, cool. Sorry, my volume was a little low. Okay, next one here. This says that wine goes bad soon after opening because the ethanol, so here I give you the formula for ethanol. Ethanol in it reacts with oxygen gas to form water and acetic acid, which is also the main ingredient in vinegar. What mass of oxygen gas is consumed by the reaction of 1.82 grams of ethanol? So again, here we first need a balanced equation, right? So we have ethanol, C2H5OH, and it's reacting with oxygen gas, right? And we know that we write oxygen gas as O2 because oxygen is one of the diatomic elements, right? So it always has that subscript of 2 in its elemental form. So then it reacts, it produces acetic acid, so CH3COOH, and it also makes water. Okay, then you would have to look to make sure the equation is balanced. It already happens to be balanced, so we don't have to do any extra steps there. So now we can deal with the math, right? So what mass of oxygen is consumed in this reaction by reacting 1.82 grams of ethanol here, right? So we're just going from the grams of ethanol to the grams of oxygen. So we start here with 1.82 grams of ethanol. Okay. Again, we have to convert that into moles, right? So to go from grams to moles, we have to divide by molar mass. So the molar mass is 46.07 for 1 mole of ethanol. So now that I'm in the moles of ethanol, right, I can use that to get to the quantity of oxygen, right? So we'll use the molar ratio to go from moles of ethanol to the moles of oxygen. And we just happen to have a 1-to-1 ratio, right? And let's just cancel the units as we go. So the grams of ethanol go away, moles of ethanol go away, and then from the moles of oxygen, we can go to the grams of oxygen by using molar mass. So we know that 1 mole of O2 is 32 grams. Right, so you work that out. You should calculate about, I have 1.26 grams of oxygen. All right. Number three says that methane gas combusts under exposure to a heat source. Calculate the moles of water vapor from 1.5 moles of methane. So this is something you absolutely have to know. And the key word here is combust, right? So you need to know that a combustion reaction, it involves a hydrocarbon, like methane, burning an oxygen, and it makes carbon dioxide and water. So we have methane gas reacting with oxygen, and it produces carbon dioxide and water. Okay, so I'm saying to calculate the moles of water vapor, from the 1.5 moles of methane. So this one is much easier because it's just straight mole to mole, right? So 1.5 moles of methane, right? I want to convert that into the moles of water just by using the mole ratio. So in this balanced equation, we have 2 moles of water per 1 mole of methane. So 1.5 times 2 is going to be equal to 3 moles of water. All right, any questions from the first page here? And if you like get lost while I'm talking, you can just speak up and I'll explain.
I think I'm good. Thank you.
Okay, cool. So we'll move on to page 2 here. I'll give you a minute to look at number 4 and try and start it on your own, and then we'll walk through it in a couple of minutes. All right, how are we doing so far on number 4? Um, I guess we could start to go through it. So this one says that compound A reacts with compound B to form only one compound. So sorry, it compound A reacts with compound B to form only one product, which is product C. Product C has a percent yield of 44%. Suppose 6 grams of A are reacted with excess compound B, and 3.1 grams of compound C are successfully isolated at the end of the reaction. So this has two parts. Part A, I'm asking what was the theoretical yield of C, and B, how much compound B was consumed by the reaction. Okay, so the big hint here is you have percent yield, right? So you know the equation for percent yield It's your actual yield. Let me write this aside. So percent yield, right? We know it's your actual yield divided by the theoretical yield times 100. Okay, so as a reminder, the actual yield is what you actually obtain at the end of the experiment, whereas a theoretical yield is the maximum amount of mass that would be permitted through doing the stoichiometry. Okay. So let's figure out how to solve for A. I need to figure out the theoretical yield of compound C. So that means that I have to be given the percent yield and the actual to be able to calculate this, right? So we have a percent yield, 44%, and then I say that the 3.1 grams of product C were I successfully isolated. So that means that this has to be the actual yield, right? Now, to do this, right? This times 100 at the end of the equation is should just make this into a percentage, right? So we have a percentage already. To do the math, we just have to undo this percentage, right? Right, a percentage is out of 100, right? So 44 divided by 100 is just 0.44. So the percent yield is 0.44, and it's equal to the actual divided by the theoretical. So the actual we have, right, which is 3.1 grams. Theoretical yields we have to figure out. So that's X. Okay. Now we can just do a little bit of algebra to solve for X on the denominator of this equation, right? We can do some cross multiplication. So put the 0.44 over 1. You do 3.1 times 1, which is just 3.1. And that's equal to 0.44 times x, which is 0.44x. Solve for x, we divide both sides by 0.44. And x, let's move it. Oh, I'm sorry about that. So we divide both sides, right? So 3.1 divided by 0.44, x is equal to 7.0 grams for the theoretical yield. Okay, so this theoretical yield, this 7 grams, this represents the maximum amount that could, theoretically be made. But just like the whole thing with percent yield, it's a way to, in a way, it's just percent yield pretty much is a way to see how good you were at your reaction, right? If I calculate that I could make 7 grams of product C, right? That's if in a perfect world, if everything goes right. Um, I'm not sure if you're in a lab now, but oftentimes you are never going to make your theoretical yield as the actual yield, right? Because you have incomplete reactions, right? You might knock over your beaker or something, right? There's, a million things that go wrong in the lab. So, yeah, that's really what the idea is, okay? Now, part B says how much of compound B was consumed by the reaction. Okay. Um, this is really easy. So you just take your theoretical yield, right? Now, um, the key here is that I say compound B was in excess, right? So compound A was my limiting reactant, and I had leftover compound B, right? So how much compound B is going to react? It's only going to be the amount of compound A that actually reacts, right? So all you do is take your theoretical yield, which is 7, which is what we just calculated, subtract it by the starting mass of A, and you'll see that 1 gram of compound B was consumed. Okay. All right. Number five. So this drawing below shows a mixture of molecules. So we have these white and red. So the white is hydrogen, red is oxygen. And suppose this chemical reaction happens in this mixture. So we have the formation of water, right, from hydrogen and oxygen, the white and the red. So A says of which reactant are there the most initial moles? B says of which reactant are the least initial moles? And C says which reactant is the limiting reactant. So I'll give you a minute to look at this diagram, get some answers for those three, and then we'll go through them. All right, so let's start to go through number five here. So part A, which reactant are there the most initial moles? That would be the hydrogen. Right, you just count up, there's more hydrogen here than there is oxygen, right? Which reactant are the least initial moles? Same idea. There's less oxygen here, right? And so here we have our balanced equation, right? So just say we could make up numbers here, right? Say you have 1 mole of H2 that reacts to make the water. We can just calculate, we can go from the moles of each of these reactants to the moles of this product, and from there we can figure out what's limiting, right? So converting from moles of hydrogen to the moles of water, we use the mole ratio to do that. So we're just using 1 mole of each reactant just to make it easy. You could use whatever number you want on the exam. So 1 mole of hydrogen is going to produce 1 mole of water. Let's see what happens when we do it with the oxygen. So we have 1 mole of O2. So 1 mole of oxygen will make 2 moles of water. So what's the limiting reactant here? It's going to be the hydrogen, right? Because the limiting reactant, it right determines how much product you can make. right? So from doing this, we see that hydrogen runs out first. So that's why it's the limiting reactant. And so we'll only actually make 1 mole of water. Okay. Number 6 says the stomach has a low pH, which is around 2, due to the hydrochloric acid present. However, after a meal, food initially neutralizes the acid, pushing the pH up to 5. Considering this, what would be the hydronium concentration of your stomach acid after having a large meal for dinner? So all this question is asking you to do is go from pH to the hydronium ion concentration. Okay, so I want to know the hydronium ion concentration after you have a meal. So I want to use this pH of 5. Okay, so you need to know that pH is a logarithmic scale, right? You probably heard of logarithms in your math classes. I'm probably spelling that logarithm. That's probably spelled wrong, but whatever. So you need to know that the logarithmic scale, um, you might remember this, that a logarithm has a base 10, right? So if I have this number, right, in pH, it means it already has that base 10 like put into it, right? So to go from pH to the hydronium concentration, I have to undo the logarithm, right? So in other words, I have to undo that base 10. So to go from pH to the hydronium concentration, you're going to take the number 10 and you raise it to the negative pH. So 10 to the negative 5 is equal to 1 times 10 to the negative 5 as the hydronium ion concentration. Remember concentration, we also use molar, capital N. Okay, number 7. This says aqueous sulfuric acid reacts with solid aluminum hydroxide. Suppose 78 grams of sulfuric acid is mixed with 32 grams of sodium hydroxide. Calculate the maximum mass of sodium sulfate that could be produced by this chemical reaction. So this is going to be a limiting reactant problem. Okay, so just looking at the words that we have here, right? We have sulfuric acid and we have sodium hydroxide. We know this is an acid-base reaction. Acid-base reaction, you need to know that it produces water and it produces a salt. Okay, so we have sulfuric acid, which is 8H2SO4. This is one of the strong acids that you are responsible for knowing and memorizing. Reacting with sodium hydroxide, which again, this is a strong base that you need to know. And it produces, remember, acid-base reactions, they make water and salt, right? So it makes water and it's going to make a salt, which is going to be the sodium sulfate. Then we have to balance the equation, so just put a coefficient of 2 in front of water and in front of the sodium hydroxide, and we have a balanced equation. So, with the limiting reactant problems, right, you have to calculate from the starting amount of each of these reactants to figure out what is going to limit how much product you can make. Um, I specifically say to calculate the maximum mass of the sodium sulfate. So I'm going to go from the grams of sulfuric acid and sodium hydroxide to the grams of the sodium sulfate. Okay, so let's start with sulfuric acid first, where we have 78 grams of that. And we're going to the grams of sodium sulfate. So we are going to go from grams to moles here. Now that I'm in the moles of the sulfuric acid, I can go to the moles of sodium sulfate and then to the mass of the sodium sulfate. So going from mole to mole, again, we have to use the molar ratio. So we have a 1-to-1 ratio. Now that I'm in the moles of sodium sulfate, I can go to the grams of sodium sulfate by again using molar mass. So the molar mass for sodium sulfate is 142.04 grams. So for the sulfuric acid, 78 divided by 98 times 142, you will get 112.96 grams of sodium sulfate. Okay, so that's half the problem. Now we have to do the same thing for our other reactant, which is the sodium hydroxide. So I tell you, we start with 32 grams of that. We go grams to moles. So the molar mass is 40. So the grams of NaOH go away. Now I'm in the moles of sodium hydroxide, and I want to get to the moles of sodium sulfate. And again, we do that by mole ratio. So here we have a 1-to-2 ratio. And then finally, from the moles to the grams. So 32 divided by 40 divided by 2 multiplied by 142, you will get 56.816 grams sodium sulfate. Now, so before we deal with sig figs, looking at the numbers, right? Sulfuric acid makes 112 grams or about 113 grams, whereas sodium hydroxide makes 56 grams, right? So 56 is obviously smaller than 112 is, right? So sodium hydroxide is the limiting reactant. Okay. Then you would just input this in the computer as 57 grams because you need two sig figs. Okay, number 8 says 79 grams of zinc reacts with 163 grams of hydrofluoric acid. Determine the limiting reagent. So I'll give you a couple minutes to do that one on your own, and then we'll go through it. So it's the same idea as the last problem. All right, so let's go through this one. Now, something I didn't mention before, the good thing about limiting reactants, whichever reactant is your limiting reactant, it's going to limit both the products you can make. So you can, it's up to, if the problem is not specific, it's up to you to calculate. You could do this one or you could do this one. Um, when I do it, I did it to the hydrogen just because the mass is easier to calculate. All right, so we have 79 grams of zinc here. So we're going to go from grams to moles. So now from the moles of zinc, like I said, we're going to calculate to hydrogen because the molar mass for hydrogen is easier to calculate. Um, so we have a 1-to-1 ratio here, and we can go a step further to get the mass. So 79 grams of zinc will give you 2.41 grams of hydrogen, and then we'll do the same thing for the HF. So from the grams of hydrofluoric acid to the moles of hydrofluoric acid, then from the moles of hydrofluoric acid to the moles of hydrogen, and then finally from the moles of hydrogen to the grams of hydrogen. So 163 grams of hydrofluoric acid will give you 8.15 grams of H2. So from here, 2.41 is a smaller number, right? So that means zinc is the limiting reagent.
For this problem, do you technically need the actual mass of each reactant, or could you just do it like you did the other problem?
Um, the mass of each, what do you mean by that? The mass of you have to use the mass of each reactant, yeah. So like you see, we did it twice, right? For this one and for this one.
Yeah.
Is that what you were asking?
Well, I just thought that if you had the problem, like the equation, you could just use the ratios and hypothetically say that you have, well, never mind. Sorry, you don't have 1 mole of each. Never mind. Okay, I get it. Sorry. Thank you.
Okay, cool. Okay, so the next one here, so this says that a chemist dissolves 635 grams of pure perchloric acid in enough water to make 400 milliliters of solution. And your job is to calculate the pH of the solution. So we talked about pH a little bit earlier, right? We know pH is equal to the negative logarithm of the hydronium ion concentration. Okay. Remember, concentration, this is molarity, right? We know molarity is equal to the moles divided by the liters. So what we have to do from the information provided, right? We have mass, we have a volume, 400 milliliters. We have to figure out the molarity of the hydronium, and then we can figure out the pH. Okay, so again, for molarity, M is equal to moles divided by the liters. So I'm given the mass, 635 milligrams, right? And we have to go first from the mass to the moles, right? However, we know that we cannot use milligrams, we have to use grams, right? So 635 milligrams, convert that into grams. it's going to be equal to 0.635 grams of perchloric acid, HClO4, right? So now I have the perchloric acid in grams. Now I can get to the moles, right? So we can just divide by the molar mass. So 1 mole of perchloric acid is 100.46 grams. So 0.635 divided by 100 is 0.00632 moles. So we have the numerator of this, right? Now we have to figure out the liters. So I give you 400 milliliters. Um, Converting from 400 milliliters into liters, we just divide by 1,000. So 400 milliliters is going to be equal to zero point 0.4 liters, right? So let's get the concentration here. So molarity is equal to the moles divided by the liters, zero point 0.4 liters. When you get that, your concentration is going to be equal to 0.0158 molar, right? Now that I have the concentration of hydronium, we can just find the pH by taking the negative log of this number. So pH is the negative logarithm of your hydronium concentration, so negative log of 0.0158, and you will get a pH of 4.14. Okay, questions with that one?
So on or in my meeting, they said that there's weird like sig fig rules with the pH and the log. So because there's three sig figs in the molarity, does that mean that you'd have to have three decimal places on the
Yeah.
H?
Yeah, actually, good point. I forget about, yeah. With with logarithms, yeah, it follows the decimal points. So I guess we have nothing here after the decimal, so I guess you could just say it's 4. But yeah, I would definitely double check on Alex like how it wants the number in there. All right, number 10, in the chemistry laboratory, you have 10.5 milliliters of 2.61 molar aqueous potassium iodide. You must dilute the solution until the concentration falls to 2 molar. Calculate the final volume in milliliters. So this is a dilution problem, right? And we know the dilution equation is M1 times V1 equals M2 times V2. So the initial concentration times the initial volume is equal to the final concentration times the final volume. All right. We're calculating the final volume. So we're gonna plug everything in that we have. So M1 is gonna be the 2.61 times V1, which is 10.5 milliliters. And just a point about about dilution here. The volume, it could, so like how we just did molarity, right? The volume has to be in liters, but for dilution here, the volume could be either milliliters or liters. It doesn't matter, it just has to be consistent on both sides. So that's M1, that's V1. M2 we have, which is 2 molar times final volume I'm solving for. So we just do some math here. 10 and a half times 2.61. You get 27.405. That's equal to 2 times x, which is 2x. And then we're solving for x, so just divide both sides by 2. You'll get x is equal to 13.7, and it's milliliters, right? Because we used milliliters on this side. It's got to be the same here. Okay, number 11 here says that aspirin, which is acetylsalicylic acid, is commonly used to treat fever, pain, and inflammation. It's produced from the reaction of salicylic acid, which is this, with acetic anhydride, and it produces aspirin and acetic acid as a byproduct. So this equation is already balanced as it is. So I am interested in the formation of aspirin. Suppose 1,000 grams of salicylic acid is reacted or mixed with 1,000 grams of acetic anhydride. And I have a three-part problem for us to answer. So part A, which reactant is limiting, which reactant is in excess, identify the theoretical yield, and then find the percent yield. So I'll give you about 5 minutes to look through that and start it, and then we will go through it. All right, any questions so far? I'll start to go through number 11. Okay, so we say we're interested in the formation of aspirin, right? So we're going to go from the grams of each of these reactants to the grams of aspirin. So let's do it for salicylic acid first. So I have 1,000 grams. So we'll go from the grams of salicylic acid to the moles of salicylic acid by using molar mass. And like I said before, the equation was already balanced, so that saves us some time. So now from the moles of salicylic acid to the moles of aspirin by using the mole ratio. And then from the moles of aspirin, we can go to the grams by using molar mass. So when you calculate that, you will see that the 1,000 grams of salicylic acid makes 1,000 1,304.34 grams of aspirin. And because it's a limiting reactant problem, we have to do the same thing for our other reactant. So now we have for acetic anhydride, 1,000 grams of that also. So grams to moles here. And again, from going from the acetic anhydride to the aspirin, it's a 1-to-1 ratio. And then finally from the moles of aspirin to the grams. So doing this calculation, you'll see that the 1,000 grams of acetic anhydride will yield you 1,764.7 grams of aspirin. So which reactant is limiting, which is in excess? So salicylic acid is the limiting reactant, right? Because it made the least amount of product. And then acetic anhydride is in excess. So in this reaction, all the salicylic acid will be used up and we'll have leftover acetic anhydride. Part B says to identify the theoretical yields of the reaction. So remember earlier I said that the theoretical yield is the maximum amount of mass that is allowed by your limiting reactant. So our theoretical yield is the 1,304.34 grams. And then finally, part C says in a pharmaceutical plant, the actual yield of aspirin is 1,112 grams. What is the percent yield? So we have to figure out percent yield. So remember, it's the actual yield. So that's the 1,120 divided by the theoretical yield times 100. When you do that, you will get there is an 86% yield of aspirin, which is like really good, right? Like I was saying before, you're pretty much never gonna get 100% yields, right? There's so many things that go wrong. Um, but an 86% yield is it's really good, right? If you had, say, if you had like if this pharmaceutical plant, say if it was like a 20% yield, that would not be efficient, right? Because then it means you're probably like, right? Because aspirin it's a drug, right? You're selling it. If you had a low percent yields, you're probably going to be spending more money on the equipment and stuff than you will selling it. So, yeah.
Hi, sorry. I have a flight in like 2 hours, so I have to go pack. But thank you so much for all your help in the first half.
Yeah, of course. Have a safe flight. Have a fun trip.
Thank you so much.
Yeah. Okay, then number 12 here, we're filling out this table. So you're either provided the hydronium concentration or the pH, right? So for solution A, provided the hydronium concentration, to get the pH, just take the negative logarithm. So pH is equal to 8.05. Solution B, you're provided the pH, so just take 10 to the negative pH to get the hydronium concentration. That will be 7.6 times 10 to the negative 7. And then for C, get the pH from the concentration, it's 5.29. 13 says a solution of barium chloride is produced by measuring 5.27 micromoles of barium chloride into a 400 milliliter volumetric flask and filling the flask to the mark with water. Calculate the concentration in micromoles per liter. Okay, so I want micromole per liter. So micromole on the numerator is good, but I want liters on the denominator. So the concentration is 5.27 micromoles divided by 0.4 liters equal to 13.2 micromole per liter. 15 here, this says you have two beakers set up, which have pH meters immersed in each of them. Beaker 1 reads pH of 3, Beaker 2 reads a pH of 7. How many times more acidic is the solution in Beaker 1 in comparison to Beaker 2? So there's a difference of 4, right, in between them, pH of 3, pH of 7, but remember it's a logarithmic scale, so it's 10 to the 4. So C is our correct answer, that Beaker 1 is 10,000 times more acidic than Beaker 2. 15, this says a 20 milliliter sample of a strong diprotic acid is titrated with 0.52 molar sodium hydroxide. After the procedure, it's found that 37.6 milliliters of the titrant was used. What was the concentration of the diprotic acid? So we're going to go ahead and write our balanced equation. So we have an unknown diprotic acid. So we'll call that H2X plus NaOH gives you water and Na2X. And then you have to balance it. So for this problem, we want to figure out the concentration of this acid from the information we're given about this base, right? So we're looking at concentration, right? So M is moles over liter. And we know to start with sodium hydroxide because we have the most information for that, right? We have concentration, we have volume. So with concentration and volume, we can figure out the moles of sodium hydroxide. From there, we can use stoichiometry to get the moles of the acid. And then since we have the volume of the acid, once we get the moles, we can get the concentration of that. So 0.52 molar, it's X amount of moles divided by 0.0376 liters. You solve for the moles. So X is equal to 0.0195 moles of NaOH. Now that I have the moles of the base, I can get the moles of acid by using the mole ratio. So we have a 1 to 2 ratio. So when you do that, you will calculate you have 0.00975 moles of H2X, which was the unknown acid. And now we can get the concentration of that. So we take the moles, which we just figured out through stoichiometry, divided by the liters, which we have, right? Convert milliliters into liters. So 0.02 liters. And you'll get that the concentration of the acid is equal to 0.49 molar. 16 says what volume of 2.5 molar hydrochloric acid will react with 11.8 grams of solid zinc? Okay, so again, we're going to use M is moles divided by liter here. So we can start with the 18 grams of zinc and convert that into the moles of hydrochloric acid. So first we go from the grams of zinc to the moles of zinc. And then from the moles of zinc to the moles of hydrochloric acid. So we'll get that we have 0.36 moles of HCl. And then from there, we can plug it into the molarity formula and figure out the volume. So 2.5 molar is equal to 0.36 moles divided by X amount of liters. You solve for X. X is equal to 0.14 liters HCl. Number 17, this says nitrogen and hydrogen react to form ammonia in the Haber process. So suppose that 7 moles of nitrogen and 1 mole of hydrogen react in an industrial reactor. Suppose as much as possible of the nitrogen reacts, calculate how much will be left over. So we're going to calculate the moles of both reactants to the moles of our product. And so this problem says that you have to suppose all of the nitrogen reacts, right? As much possible nitrogen reacts. So if we have 7 moles of nitrogen reacting, Just subtract it by the limiting reactant, right? So you'll get that um 6.33 moles of N2 are going to be left over in this reaction. Number 18, calculate the volume in liters of a 0.058 millimolar iron 2 bromide solution that contains 125 grams of iron 2 bromide. Okay, so we're given this concentration in millimolar, but we have to convert it into molar, right? So just divide this here by 1,000, and you'll get that you have 58 molar. And we want to find the volume of this, right? So we know it's moles over liters, right? So I have capital M. I need to figure out the moles, and then I can get the volume, right? So I'm given the mass of the solution. So we're just going to divide that by its molar mass. And then from there we can plug in, right? So 58 molar is equal to the moles divided by liters. Solve for X, and X is equal to 0.010 liter. Number 19 says that the concentration of chromium 3 ions is 0.24 molar in a solution of chromium 3 sulfate. What's the concentration of chromium 3 sulfate in the solution? Okay, so I have 0.240 molar of chromium ion, and I want to figure out the overall concentration of this solution, right? So you would have to write out the formula for this compound, right? And you'll see that when it ionizes, 1 molar of the chromium 3 sulfate has 2 moles of the chromium ion. That way the chromium ion cancels and you're left with the chromium sulfate. So you should get 0.120 molar chromium 3 sulfate. Finally, number 20 here, 10.9 grams of gaseous methane burns in the air, reacting with 77 grams of oxygen. Find the maximum mass of carbon dioxide that could be produced in this chemical reaction. So this is another limiting reactant problem. So we have methane burns in air, makes water and carbon dioxide. So we'll start with the mass of methane. So when you calculate the mass of methane to the mass of CO2, it's 29.97 grams of CO2. Let me do the same thing for oxygen, where we have 77 grams of O2. Go grams to moles. from the moles of oxygen to the moles of CO2 by the mole ratio, and then finally to the grams. And so the maximum mass we can make is the 29. And I said to round it to 3 sig figs, so you'd say it's 29.9 grams of CO2. Okay, and that's all for exam 3 on stoichiometry.